This is the second installment in a series of 4 lectures that have to do with the ramifications of quantum statistics and how it plays out in the behavior of light in cavities, the emission of light from surfaces, the properties of electronic materials, and even the behavior of stars. In this part of the lecture, I'm going to talk about what we call the photon gas. The sources for this portion of the lecture are actually Crane, Chapter 10, with which you should be familiar by now from reading about quantum statistics, but this is the continuation. And Townsend, the 6th part of Chapter 7. Townsend packs a lot of material into Chapter 7. And for further reading, Iceberg and Resnick, Chapter 11. At the end of the last lecture, we were talking about the idea of the density of states as the density of states per unit energy in a system. It can be found from the density of states in K-space, and in K-space, the momentum states, the K states, momentum states, are spaced equally throughout space, through the K axes. And once we know that, then we can calculate the density of states as a function of the magnitude of K. And it's only dependent upon the dimensionality of the situation. We're going to talk primarily about the 3-dimensional case here, real world, let's say. And now we have the particular case where we know the relationship between the energy and the wave vector, the magnitude of the wave vector, and that allows us to deduce the density of states as a function of energy as opposed to wave vector. And for that, again, we make the substitution of energy for wave vector with the appropriate relationship, where energy is equal to h bar k, or k is equal to E over h bar. And therefore, dE dk, the derivative of the energy with respect to the wave vector, is just h bar. And we plug that all back in here, making this substitution for the density of states in K space, making that substitution there, substituting for energy here, and dividing by the derivative. And that leaves us with this: the density of states as a function of energy for photons is the volume of the actual real space, the real box that we have. And in this case, we've assumed that the electric field must go to 0 at the boundaries of the box, which tells us what the wavelengths in the box are permitted to be. And when we do that, we end up with this relationship. The real volume of the box, so the larger the box, the greater the density of states. Energy of the photon in the box squared, right, divided by constants that come out of taking these various substitutions and derivatives for the density in K space, and the relationship between energy and wave vector. To go through it again, just so that you can see it, we assume a rectangular cavity with dimensions Lx, Ly, Lz, and then we calculate the magnitude of K from that. The states are evenly distributed in K space, and that means that the number of states with K less than some maximum value of K, just taken as an example, the number of states is 4/3 pi K cubed for the maximum value of K that we chose, divided by the volume per state in K space, right, with K, all right, and this is the volume in K space, and that's the volume in real space of the sample, So we can make these substitutions here. Making that substitution in K space leads us to this relationship here, that the density of states in K space as a function of the magnitude of K is equal to 8 times the volume of the box that we have divided by pi squared times k squared dk. We've multiplied in an extra factor of 2 here because there are 2 polarization states for light traveling. If you think about linear polarization, any light that's polarized in some direction, that's moving in some direction, can have 2 orthogonal polarization states. So the factor of 2 comes from that. Normally, we don't talk about black body radiation or optics in terms of the wave vector. Normally, we talk about wavelength or energy, photon energy, or light frequency, most frequently wavelength and energy. Right? So we want to convert this density of states into a spectrum of states, a density of states for each of those types of measures. So making that substitution, remember all that we're going to do here is that we start out with this density of states, and then we're going to convert it. And the way that we convert it is by making a substitution of frequency for wave vector, and they're going to be directly related to one another, all right, in a fairly straightforward way. That's in here, all right. K is equal to 2 pi times the frequency divided by the speed of light, and that's a k squared in there, so that's the factor that we've got there. And then we need d nu dk, and if the relationship has a nu squared in it, then we're going to end up with this as our derivative with respect to k to make the substitution, which leaves us with this, that the density of states in frequency space is 8 pi times the volume of the box divided by c cubed times frequency squared. I could have found that by deducing this for the energy density of states, which we did on the previous page, and we had an E squared, and we know that energy is equal to H times nu, so that's where these additional factors come from here. So I could have made that substitution here. Energy equals H nu, and then you divide by H cubed in order to switch frequency to energy. Or, maybe more interesting, we can calculate the density of states as a function of wavelength. So remember, this here would be the number of states in a wavelength range about wavelength lambda, and the wavelength range would be d lambda. So this is actually a number of states here, and d of lambda is the density of states. So making that substitution between wavelength and wave vector, because wave vector is 2 pi over lambda, we make that substitution and take our derivatives, and we end up with this relationship here. That is, that the density of states in wavelength is 8 times the volume of the box over pi times lambda to the 4th power, the wavelength to the 4th power. There's an additional factor of 8 that's taken out here because wave vector can be positive or negative. It can point in any direction, but frequency and photon energy can only be positive, and the same for wavelength, it can only be positive. So we have to count up the number of quadrants and divide by that in order to get the density in wavelength or energy or frequency. The number that is going to be interesting to us to work out what the spectrum of light coming out of a hot body would be, all right, is to work out the energy density per unit volume at finite temperature, with the idea that we're going to have, and this is why it's called cavity radiation, that we're going to have a container, a box, which has got a very tiny hole in it. And in here, it's going to be hot. So this is a cavity with walls, like so. And we're assuming that at the walls, the electric field goes to zero. Let's say that these are metal walls and that they are reflecting. As a result, the electric field goes to zero. The transverse electric field goes to zero at these walls. And we have the same rules that we had for the wave vector in the space. That is that the ground state wavelength might look like that. The mode that might exist in this box might look like that. And then I'll have all the other modes as well. And all of these modes of light are traveling around in all directions. And they're bouncing off the walls. And they just continue to bounce off the walls, reflect off the walls, until some tiny fraction of them come out. So what we want to know is what's the energy density in here, and then that energy is traveling in all sorts of directions. And we'd like to know what fraction of it comes out. And we'll measure that fraction as a function of energy, or the energy of the photons, or we measure it as a function of wavelength of the photons. The original measurements were done as a function of wavelength. So the density of energy in the box as a function of energy, all right, is going to be the density of states, which we just calculated, times the energy per photon, all right, times now the question is how many photons do we have in each of these states? We've got a density of states, but each one of these states has a different number of photons in it, and that's what N of E yields. For a Bose gas, for bosons, that occupation function as a function of energy looks like this. This is what we derived before, all right? As you can see, there are no zero energy photons in here, so this never makes it to infinity. But for long wavelengths, this can get large. So our energy density is the product of the volume here is in order to, because we're measuring an energy density per unit volume, all right, is the energy of the photons at a particular energy, right? Density of states at that energy, occupation function at that energy. That's the density of energy, the energy density. So we put all of that together, and there's an extra equal sign here. That shouldn't be there. We put all of that together, and we get what is called the Planck distribution function. That's the distribution of energy per unit frequency per unit volume in the box. And that's going to be proportional to what comes out of the box. So again, I've got a cavity. I've got a density of energy per unit volume in here. That energy is moving around in all directions, and some of it comes out. And we measure, don't necessarily do this with your eye. There's an eye there looking here. We observe the energy that's coming out, and we say, hey, what color is that? And that tells us something about the wavelength, right? So the energy density as a function of optical frequency is this, just making all the substitutions, the density of states, the occupation function, and the density of states in K space, and then making the substitutions for that. And we end up with a function that has this behavior here. So I'll take the highest temperature here, right? And you see that it's a spectrum with a peak in it that falls off to zero at a very low frequency. So in the far infrared, it falls off to zero because the number of modes per unit volume decreases as we go to longer and longer wavelengths. And at very high frequency drops off to 0 because the exponential in here begins to pull this back down. So this function here drops off principally exponentially at high frequencies, and at low frequencies it drops off as a power law of V, because this ends up approaching for a small frequency, this ends up being linear in frequency, so it drops off as frequency squared. And the total energy that comes out is going to depend upon the temperature as well. As a function of wavelength, we get a curve that looks sort of similar, but actually it's not surprising. It falls to 0 at 0 wavelength. That would be high frequency. It goes to 0. And it goes off to 0 at very long wavelengths, again, because the number of modes per unit volume drops off, that nu cubed there, or in this case, wavelength to the 5th power, after we've made all of the algebraic substitutions. Okay, so this is the thing that we most frequently measure. We set up a spectrometer, and the spectrometer will frequently just have a grating in it, and the grating splits the light that's coming in into different wavelengths, and the amount, the wavelength range that comes out of the slit in the monochromator tends to be nearly constant, and as a result, what we're measuring with a grating monochromator or spectrometer is the density of modes as a function of, the energy density as a function of wavelength. So this is always energy density, but it is energy density as a function of wavelength. So that relationship has some simple behaviors that we can extract. The first one we'll talk about is so-called Stefan-Boltzmann law, that relates the total energy coming out of a black body cavity versus temperature of the cavity. The second one is the Wien displacement law, in which the peak wavelength that is observed for the black body or cavity radiation varies as a function of temperature. And then we have some specific examples that are some nice, useful examples of these effects. So it's sort of been mathematics up to this point, but now we talk about what we observe. So Stefan-Boltzmann law relates the total amount of energy coming out of a cavity to the temperature of the cavity. So let's take a look at that. If we want the total amount of energy, then what we do is integrate the energy density per unit frequency, so energy density as a function of frequency, or we could do it versus energy as well, from 0 frequency, very low energy, to infinity, high energy. And the function that we're integrating over is this Planck distribution relationship here. To make it sort of obvious what the result will be, what I'm going to do is make a substitution, a U substitution, where U is h nu, again that's frequency there, divided by Boltzmann constant times the temperature, so that factor there. And then when we make the substitution, we need to pull out a whole bunch of constants in order to make the integral as straightforward as possible. We just pull them out of the integral. All these things are independent of the thing that we're actually integrating here. So integrating from 0 to infinity, u cubed du, e to the u minus 1. This integral here is a definite integral that can be looked up. It's got the value of pi to the 4th over 15. And therefore now we actually know the total energy that is coming out of a black body radiator. How do we measure the total energy? Actually, very frequently what we do is we've got our radiator here, light coming out like so. We put a collection system, and that collection system goes onto a little black object that's got a thermometer on it. And we measure the temperature on this object here, which tells us the temperature rises because it is being heated by the light that comes out. And by the change in temperature, we can measure how much total energy is coming out and being absorbed by this object. You've all experienced it when you walk across a blacktop that has had sunlight shining on it, and the blacktop gets hot, and from the heat of the blacktop, we can deduce how much energy was incident upon it from the sun. Okay, so repeating a little bit of what was on the previous page, just so that we get the words. We have this energy density inside of the black body, and then that energy density results in light coming out, and that light actually comes out over some range of angles, like so. We measure the total energy that comes out, and we can measure the amount that comes out per unit area on the surface, and that is called the spectral radiancy. And that's frequently what we measure. The total radiancy is the integral over all frequencies, just as we had on the previous page. And when we then analyze that, or rather simplify that so that we have just one constant times the temperature dependence, then we have a constant in here that is called the Stefan-Boltzmann constant, and it relates the total amount of energy that comes out of a surface to the temperature of the surface if you have a perfect emitter, like a black body. Everything from the inside here that arrives at that surface leaves. And the Stefan-Boltzmann constant just comes from the variables that we had on the previous page, and it turns out when you compute it to be 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the 4th power. A second important measurement that we can make is one that yields the temperature of the object by measuring the wavelength at which the peak in the spectral radiation comes out. You measure the wavelength or the frequency, but the relationship that is most frequently used is the wavelength, and the shift in the wavelength at which the peak occurs. So we look here, you see as you lower the temperature, the wavelength goes to longer and longer wavelengths, and that can be found by inspecting the Planck distribution law and taking a derivative of the energy, of the spectral energy coming out as a function of wavelength. You set the derivative equal to 0 at a given temperature, and we find that there's a simple relationship, right? That the wavelength at which the peak occurs is a constant, in this case v, divided by the temperature. That is, that the wavelength shifts with temperature. Frequently, this is written as lambda peak times temperature is equal to a constant, where that constant is, again, just a number, 2.9 times 10 to the minus 3 meter Kelvin. So it predicts what the wavelength will be. So if we can measure the spectrum of light coming out of a hot object, then we can measure the wavelength at which the peak occurs. And if we know that, then we know the temperature. This is actually the way that many temperature sensors, modern temperature sensors, even the sensor that you point at your forehead to measure your body temperature, this is the way they work. And some of the more sophisticated ones measure the wavelength. Others measure the total energy emitted from your forehead, for example, and deduce the temperature using the Stefan-Boltzmann law. So these two techniques are the standard ways of measuring the temperature of an object. As far as another aspect of physics that many of you are interested in, the spectrum of light that is observed coming out of an object like the sun is also very nearly mirrors the black body spectrum. Now, the reason that the actual spectrum that comes out is different is because the sun is not a cavity with light coming out of one tiny hole in the cavity, but it's actually a plasma that has atoms in its outer atmosphere, and those atoms can absorb, and the way in which the atoms emit and absorb and the plasma emits and absorbs can change the spectrum somewhat. But overall, the spectrum that comes from the sun and arrives at the top of our atmosphere has an overall black body spectrum with a few extra wiggles in it, right? And the black body spectrum that's shown here is for a black body that's at about 5,250. Many textbooks will report the temperature is closer to 6,000, maybe 5,800 degrees Kelvin. All right, 5,800 degrees Kelvin. What actually arrives to us at the surface of the Earth depends upon absorption by molecules and atoms in the atmosphere. And so the various dips in here are due to absorption by different molecules in the upper atmosphere. The most important one to us is actually the ozone, which absorbs a lot of the ultraviolet. And that's good because ultraviolet actually denatures proteins and damages DNA. So we don't want that much ultraviolet around. We can determine the temperature of very distant objects even if we don't know how big they are or how much total energy is being emitted by those objects, again by measuring the spectrum. And here are some rather rough spectra. One for the star Spica, which is a very hot star. Our sun, 5,800 Kelvin. So I told you on the previous page that sometimes it's reported in Kelvin as 5,800. That differs by a few hundred degrees from the previous page, but we're in the same ballpark here. And then a cold star that appears red to us, which is Antares. Our use of the black body spectrum is not limited to just stars and the measurement of temperature of things on the Earth, but it actually informs us about the nature of the universe. Towards the end of this course, we'll talk more about Big Bang and cosmic expansion, and here is some of the evidence for Big Bang and cosmic expansion. If we point a telescope anywhere in the sky that doesn't have a star directly in it, in our line of sight, then, and even if we point in the direction of the star and put filters in order, such that we don't actually observe optical light, but we look in the microwave range using radio telescopes, then we find that there's a spectrum of light that is observed in every direction that we view in the universe, about us, that very closely follows a black body spectrum. In fact, the dots here are data points, and the line is the fit to a black body spectrum with a temperature of just 2.735 Kelvin, right? This is frequently referred to as the 3 Kelvin background as a rough approximation, so the 3K background. And the existence of this background, again, gives us information about modeling the structure and origins of the universe as we observe it. In the next section of these lectures, I'm going to talk about the density of states once again, and its ramifications for the behavior of electrons in materials.